when we talk about hypothesis testing, there are so many different types of hypotheses that you could run. And the whole objective is for you to walk out of here just having that 40,000 square foot view, thinking about it in terms of what is the hypothesis test that I need to run. Because if you're running the wrong test, it's like making the wrong control chart with the right data, if that makes sense. You're like trying to make an attribute chart, but your data is actually variables, or vice versa. It just won't make sense. It's just like going on a trip. That's what we're doing this week, is going on a trip through hypothesis testing. And I'm trying to give you the map so that if you were given a location of where you need to go, you could figure out the directions of where to get there. That's the way I think of it. So we're working in this space. And if I said, okay, so the challenge is we're working with data that's normally distributed, and I have two groups that I'm comparing. I want to know if one treatment gives us a bigger result than the other, more flavor or less energy consumption. We're looking at two groups. You have all the information you need, and you could, before I finish the sentence, you could say t-test. Got it. And if I said the data is not normally distributed, but we're still wanting to compare two different groups, you would say non-parametric. What's the non-parametric thing that we do when we don't do a t-test? Because we only do t-test when it's normally distributed. So you could just, bam, be as smart. And I'm trying to teach it in a way that you would have all the information you need, and you're smart. You can figure out how to figure out the calculations. But if you don't know the right test, then you're going to be ending up going down the wrong road and getting lost. Okay? So if I said we want to compare three groups and the data is normally distributed, then you would say, bingo, ANOVA testing. I know it. And if the data is not normally distributed, you say, no problem. I can look up, what's it called, the Mann-Whitney test or the Wilcox? And then you could just look at these cheat sheets I'm giving you, and you could just figure it out. You could figure out the math if you had a textbook or notes from this class. And I just want to kind of show you how to make some sense of it. So let me just, first of all, introduce how to choose what type of hypothesis to do. We're going to need to know, are the data ordinal, nominal, discrete, or continuous, before we figure out which types of hypotheses test to run. So I think you could follow this. If we had categorical data, we're thinking about categories. What group are you in, instead of numerical, which would be like moisture content or dissolved oxygen or something like that. And you know this by now. If order matters, then it's going to be ordinal, O-R-D. And that would be, an example would be a sensory scale. On a 5-point scale, where you strongly agree is 5, you strongly agree that this flavor is yummy. That matters more than, 5 matters more than a 4. If order doesn't matter, it's nominal, and you know that by now. And order of gender doesn't matter, race doesn't matter, shift, production line, those usually don't matter. But if we're looking at numerical values, we can have discrete data, where we're talking about the number of workers, the number of nonconformities, the number of nonconforming units, and you know by now what continuous data looks like. And that would be like some sort of fraction usually, or something like that. pH, water activity is between 0 and 1. Number of workers per shift. Notice how that's different from number of workers, because now we have a denominator, which would be shift. And we have number of nonconformities per sample. So as soon as you make that denominator underneath it, then it's going to be a fraction. Okay? So this, my friends, is one of my favorite flow diagrams of all time. And it is so nice. As we look at it, notice how the top colored boxes there are the flow diagrams based on whether the data is continuous, ordinal, nominal, or categorical. So I think if you were given a scenario, you could sort your way through, am I concerned about pH? Where on this map am I going to be? Going to be to the left where it's blue, right? Because that's a continuous variable. Dissolved oxygen, moisture content, things like that. And notice how all the way at the bottom, these those tell us what hypothesis test is the most appropriate one for that scenario. Let's say I want to compare two groups. So let's say I do a pre-test. We just kind of get a baseline. How compliant are you right now with these food safety auditing standards? And then we roll out a new training intervention, and then we do a post-test evaluation of compliance, and we can see, well, did our educational intervention drive more compliance? So in that case, we can, for every single operator that went through that intervention, we can get their score before and after, their knowledge score, or we can get their plant's audit scores with either of those sets of data. We would do a paired t-test because we have 2 time points that we're wanting to compare. Notice how within each of these rectangles, the top is for the parametric. Anyone know what parametric means? And the bottom is non-parametric. And basically what that means is the top one is for when the data is normally distributed. And the bottom one is for when it's not normally distributed. So the thing that you're interested in comparing is always going to drive you to some sort of rectangle here with 2 rectangles inside the bigger rectangle. You just got to do a goodness of fit test or some sort of method. You can eyeball the histogram to see how normally distributed it looks. And don't worry, JMP just spits it out and it tells you black or white. Is it normally distributed? There's 3 or 4 different ways that we can figure that out. But this diagram here is that's our roadmap. That's all you need to get from one place to another. And notice if I wanted to compare 3 groups, then now we're looking at either this one or this one. If it's a repeated measures where I want to do like a pre-test, a post-test, and then another follow-up post-test 6 months after this training intervention, then that's going to be repeated measures. So you just got to kind of use your common sense and intuition if I kind of follow this roadmap. Whereas if I don't care about repeated measures and I just want to know, I'm just comparing independent unmatched groups, A shift, B shift, C shift, which one has most production per hour, pounds per hour, then that's going to be a one-way ANOVA. If it's normally distributed in a non-parametric equivalent would be the Kruskal-Wallis. And so once you feel comfortable using the computer, it's just a matter of asking the software, how do I do that Kruskal-Wallis? That's the non-parametric version. And JMP makes it pretty easy to do all that. Okay. Here's another visual. It asks you, are you comparing the means? In which case, it provides more elaboration than that previous diagram. The differences between the means of 2 independent groups. We're either going to do an independent t-test or a Mann-Whitney test. But if we're looking at the differences between the paired samples, like weight before and after a diet, now we're doing a paired t-test, and this would be the non-parametric equivalent. Okay, so just spend some time just kind of looking at that and thinking, well, what would be an interesting way to borrow that one? And then we get into, instead of comparing means, we can look at the relationships between variables. We want to look at the strength of relationship between 2 continuous variables. Well, there we're going to be doing a correlation. But if we want to predict the value of one variable given the value of a predictor variable, then we can do a regression. So